Hey everyone, so today we're going to be talking about the basicity of amines and arylamines. Arylamines just refers to a derivative of something like aniline or anything that has an aromatic ring with an amine that's attached to it. But this is generally what arylamines are referring to. So amines can act as Lewis bases because they are lone pair electron donors, and they can be hydrogen acceptors, right? So they can abstract hydrogen. And generally, the higher the pKa value, the more basic the amine. You could also use a pKb value, but this is used a little less common in the literature. And so you probably won't see it very much outside of textbook scenarios. And the pKb and pKa are related to each other the same way the POH and pH are related to each other. The pKa plus the pKb is equal to 14. And so generally the trend for basicity in amines is that alkylamines are the most basic, followed by ammonia, which is just hydrogen. Then arylamines are the least basic. Arylamines are going to be the least basic, which is usually due to the fact that arylamines are resonance stabilized with the lone pair there, right? So if we have an arylamine, we can have contributing resonance structures, NH2, where we have this lone pair that can then go on and donate or contribute to resonance structures within the ring itself. So something like this, and then we can move this around. Minus double bond NH2 plus. There's a plus sign there now. I forgot the double bond there. And then we can move this down here. And then now we have all of our resonance structures with the charged group there, right? So the arylamine has this resonance stabilization that is stabilized in the non-protonated version of the arylamine. And because it's stabilized by these extra resonance structures, that means that it's less likely to be protonated, right? So these are going to be a little bit less basic than, not a little bit less, quite a bit less basic than alkylamines, which are going to be the most basic, and ammonia, which has a basicity that is in that. And the reason that those are more basic is because you have kind of hyperconjugation effects of the alkyl group stabilizing that positive charge on the ammonia. And so this is in contrast with amides, which are not going to be basic because the lone pair on the nitrogen is resonance stabilized, right? So if this is our amide, this lone pair can be resonance stabilized. And this is actually why this amide bond has slight double bond characteristics, right? Because of this resonance stabilization, right? So resonance stabilization plays an important role in the basicity of amines and arylamines. And so the basicity of amines we can use to purify amines because are soluble in water as an ammonium salt or just as a protonated salt. So we'll have something like NH4 plus Cl minus, the form that it's in, and that's going to be soluble in water. And then if we add acid, that would undergo a neutralization reaction, right? The water is going to keep the ammonia or the amine compound into an aqueous layer, and the other organic material like ether or other organic neutral compound is going to go into an organic layer, right? So if we change the pH, right? So we raise the pH such that the amine is going to be completely in its protonated form, or we lower the pH as the amine is completely in its protonated form, and we generate water or add water to that solution, then the amines will stay in an aqueous layer that's surrounded by water, and then the organic material like ether, THF, hexanes, whatever else, those are all going to stay in the organic layer. And so even if our amine was originally, and this would be our separatory funnel, for example. So even if our amine was originally going to in water, we can use this method to then separate the amines from other organic materials. And once we have the aqueous layer, then we can add sodium hydroxide and ether, but therefore raising the pH, right? So if we then add, after we drain organic layer, you can add sodium hydroxide and maybe ether as your organic solvent, ether. And then what happens is as we raise the pH by adding sodium hydroxide, the NH4 converts back to NH3, or in this case, it would be so NH4 plus NH3, or if it was a larger tertiary or secondary amine, and you add ether to that, then you're going to create your sodium chloride salt, and then the amine is going to go into the organic layer. So now the NH3 will be with ether or hexanes or something of that nature. And in the top organic layer, this is going to have your sodium chloride salt solution, because now you have deprotonated the amine. Right, so now you have two more layers, and then you can separate them one more time, and you have purified your amine from both aqueous layers and from the original organic material. So you can take advantage of this basicity to purify amines, and this is used a lot, and we saw this actually in our synthesis of para-amino benzoic acid synthesis last week. And so we can look at then also the substituent group effect on the arylamine basicity. And in the same vein that we could look at that effect on acidity for carboxylic acids, we see that arylamine's basicity increases when we have a electron donating group that has been added to the ring. So an electron donating group added to the ring increases the basicity of the arylamines. And that's just because when we have electron withdrawing groups, having that extra positive charge on the ring from the protonated arylamine, right? So you think about if we have something, our protonated arylamine, something like this, we have this extra positive charge here. And if there is more electron density on the ring, then we will have activating groups, which these are going to be activating the groups for nucleophilic aromatic substitution. More electron density equals a more stable positive charge, whereas deactivating groups will have less electron density on the ring, and therefore they will deactivate the ring towards nucleophilic aromatic substitution, but also they won't be able to stabilize that positive charge as well, right? And so the basicity, it's not going to like that as much. It's not going to be as likely to abstract a proton. So it's going to be even less basic. There's amine, if we have something like a nitro group with an amino group there, then the ring will not go through any sort of electrophilic aromatic substitution. You can actually use those as solvents for other electrophilic aromatic substitution reactions. And if you had a protonated amine in that example, you see the pKa is so low that would actually act very, very acidic in solution. And so the last thing I'll mention about the basicity of amines and aryl amines is that based off of the pH of the solution and the pKa of the amino group, we can determine a fraction of the protonated or deprotonated form of the amino group. And also if we were doing this so this would be useful for purification, or if we didn't know the pKa, we could do a titration to find these values of different amines that you may synthesize. You can find the fraction of protonated or deprotonated form of the amino group. And you use this using the Henderson-Hasselbalch equation, which really just comes from an expression for the acid equilibrium constant. So if we have something like H2O, which is a liquid, plus HA, which is our generic acid, that goes to A minus aqueous, both of these are in the aqueous phase, plus H3O plus. And if we were to write an equilibrium expression for this, we get something like A minus H3O plus over HA. And if we take the negative logarithm of both of these, both sides here, equals minus log, which you guys have probably done in previous classes. We see that the log of the Ka minus log of the Ka, this is just defined as the pKa. The left-hand side or the right-hand side of this equation we can split up because a product of two things is equal to a sum of logarithm. The logarithm of a product is equal to a sum. So we have A minus over HA, and then plus the negative logarithm of the H3O plus concentration, which we know this is just defined as the pH. And so if we rearrange this equation, we get the pH is equal to the pKa plus the logarithm of A minus over HA, right? And this is defined as our Henderson-Hasselbalch equation. And so this gives us a relationship between the pH, the pKa, and the fraction, or the ratio of the protonated versus deprotonated form of our weak acid or base. So you can do the same thing. For the basic equation, if you wanted to. We can do everything in terms of the acid equilibrium constant, but if you wanted to, as a side exercise, wanted to work through the problem, you can do it with H2O liquid plus B goes to OH minus plus HB plus, right? So if you did the same thing for this type of equation and KB, you could derive the basic version of the Henderson-Hasselbalch equation. And so this Henderson-Hasselbalch equation, again, is useful because it tells us the relative amounts, the fraction of the protonated versus deprotonated form, which can be useful for buffers in our blood, for example. And so if we had a situation where we had some pyrimidine in solution, and let's say we had 0.00 molar pyrimidine, you could then use this equation to find the percentage of the protonated and deprotonated versions of the base in this solution if we have a pH of 7.3. Right, so in the Henderson-Hasselbalch equation, we have the pH. This is the pH of solution equals the pKa. This is the pKa of base. And then we have the logarithm of both of the A minus over HA here. A minus in this case is going to be the deprotonated base, so this will be pyrimidine, which will be R NH2, and then the HA, sorry, not HA minus, HA will be R NH3 plus. So we have this equation, so this is going to be 7.3 equals 1.3 plus the logarithm of both of these things, R NH2 over R NH3 plus. And then we have 0.001 molar is also equal to the sum of the concentrations of R NH2 plus R NH3 plus, and we can use both these equations simultaneously to solve for the other. So if we plug in, let's find the fraction of the deprotonated, the protonated version first. We can rearrange this to have R NH3 plus, the concentration is equal to 0.001 molar minus R NH2. We can then plug this into our expression for the Henderson-Hasselbalch equation. And so if we do that, we get, combining on the left-hand side, we get 6.0 is equal to logarithm R NH2 over 0.001 minus R NH2. We can take the log of both sides, so that'll give me E, I guess we can use 10 here because we're in base 10, so this will be 10 to the 6 is equal to 0.001 minus R NH2, and all over that is R NH2 concentration, like this. We can multiply that to the both sides. We get 10 to the 6 times 0.001 minus 10 to the 6 R NH2 equals R NH2 concentration, collect like terms, and that'll give us 10 to the 6 equals R NH2 times 1 plus 10 to the 6, which is roughly just going to be about 10 to the 6 times 0.001. Zero, zero, one, and then we divide both sides. This will roughly give us that the concentration is almost entirely going to be in the deprotonated form, right? And so we can use the Henderson-Hasselbalch to find the relative ratios of these. We could solve for this exactly if I had a 1.01, but it'll be in a very, very small fraction that will have the protonated form of the amine. And this might seem counterintuitive at first, but this is also going to be one of the aromatic amines, so it's going to have a relatively acidic behavior in comparison with the other basic amines. This pyrimidine is gonna look like that. Okay, and so this is going to be the use of the Henderson-Hasselbalch equation to find the percentage of protonated and deprotonated form. So we'll end this lecture at this point. Next time we're going to talk about the synthesis of amines, lots of reactions you've seen before. We talked about the Henderson-Hasselbalch equation today, the substituent effects on the basicity of aryl amines, the basicity of amines being used to purify amines from other organic material, and also just general trends in the basicity of amines and aryl amines.